This is a minor dissertation conducted under the supervision of Professor James Gain as part of a master's degree in computer science at the University of Cape Town, South Africa. We demonstrate a system that generates synoptic-scale clouds, so synoptic-scale meaning on a global scale, using a hybrid technique of both simulation and then procedural amplification. While this has been an active area of research for over 50 years by now, there's been almost no work on synoptic scales. So there were two different teams in the mid-2000s, so Tobashi et al. And Zhu et al. In 2006 and 2009 respectively, that had pure Eulerian synoptic scale cloud systems, but they had no topographic or oceanic effects, and these are very important for weather. No one has used a hybrid system on synoptic scales either, and most of the recent work on small and meso-scale systems, so in the last 10 or so years, used hybrid systems. We want to have synoptic-scale systems for a few reasons. So first is that in games and movies set in space, you want realistic clouds, especially over longer time periods. And this has not really been done before. So you also want to create boundary conditions for smaller scale simulations, because that's one of the biggest challenges, is to have accurate boundary conditions. And by having a global system encompassing your small scale simulation, you get rid of the need for boundary conditions entirely. You can also use it as an educational tool, so making small tweaks to explore the changes to the atmosphere. So, for example, added CO2 or added plant cover, and you can see how that will affect the weather. By using this graphics generator, it vastly reduces the computational cost compared to a full climate simulation, and therefore this can be used by most people without access to a supercomputer. We use interactive meso-scale Skyscapes by Vimont et al. As the base for our system. So Skyscapes uses a hybrid Eulerian procedural amplification system on a 50 by 50 kilometer area. Advection is handled in 2D layers, followed by convection and other 3D effects between the layers. This is computationally much cheaper than doing a full volumetric 3D advection scheme. Procedural amplification is used to generate the fine detail from our coarse simulation, and this is stuff like the type of clouds and the appearance of those clouds then. One of the biggest shortcomings of the Skyscape system is how much of the code is hard-coded, how much of the parameters are hard-coded, and how integrated the underlying grid structure is into the system. So one of our main goals was to, as far as possible, disconnect our system from the underlying grid structure. We also made sure that planetary constants, so what the atmosphere is composed of, the terrain constants, so albedo, specific heat capacity, and so on, are set by the user at runtime, and therefore you can play around with different types of planets. So how does Mars look? How does, say, Tatooine look? And it also allows us to create unit tests for each engine and model component individually, which is of great benefit if you want to swap out a unit, for example. Discretizing the surface of a sphere is a non-trivial problem. There are a few accepted methods to doing this, and we initially went with the staggered spherical grid, which ended up very unstable and tended to degenerate within less than 20 time steps. So after that we switched to the cube sphere, and that is still under construction. It has simpler advection, but much more boundary conditions and organizational complexity. So trade-offs as with all things. A necessary change now that we are on a sphere is the Coriolis effect. So the Coriolis effect is an inertial force that arises from the rotation of the Earth, and in our case, this is only horizontal movement because we're doing 2D on the surface of the sphere. It ended up being a relatively simple equation. This is something we implemented, and the jet streams and the trade winds, which can span half a hemisphere if not more, are the larger scale effects of the Coriolis effect on Earth. So this was part of our push for greater accuracy and a more detailed simulation. So Vimont et al. Used several flat approximations for interactions, especially to do with thermodynamics. Sun heating the ground heating the air, and so on. We've replaced this by proper thermodynamic models because we need differential heating, so land compared to ocean, for example, which was not present in the Skyscape system. Similarly, we also implemented the atmospheric and zenith angle influences that you need for proper latitude differences. So, for example, at the poles, you get much less sun because the sun is lower on the horizon, much more atmosphere to travel through and reflect and absorb light. This is a large part of seasonal differences as well. We also added a proper sun model, having daily changes, so day-night cycle, and also seasonal cycles. So image on the right shows how the Earth looks in July, and you can see the angle differences, how much more sun there is in the northern hemisphere compared to the southern, and that is how the seasons come about. Our system is set up to handle any number of stars with any variation of distances and luminosities, or modeled accurately, so you get something like Tatooine, for example, with 2 suns. And this is set through configuration JSON files, just like the planet information is. Our system also deals with biome assignment. So vegetation has a significant impact on the weather. You have large quantities of moisture being added to the atmosphere through evapotranspiration, and it also influences the atmospheric temperature through changes in albedo. So if we take a look at the image on the right, you can see this is taken in July, and the northern latitudes have very much green, dark green, compared to in winter, those green areas would probably be all white, and that has a massive effect on the temperature. The last component such that we added is ocean circulation. So ocean currents transport half or even more of the heat received from the sun away from the equator. So surface ocean currents are the results of winds and the Coriolis effect, and these have a big influence on the Earth's weather. So differential heating between sea ice and open ocean has big effects and one of the main concerns of climate change. Another thing is just the heat transfer, why, for example, Britain is warm compared to Canada on the same latitude. Unfortunately, the system is not yet finished. Still a month or two away from completion, otherwise I would have had a demonstration of the system here.